Think about this. The universe is 13.8 billion years old. However, wasn't time supposed to be relative? Depending upon how fast you're moving, the passage of time slows down, right? Then how did we end up with one age for the entire universe? Is it actually universal, or is it just the age as observed by us? Well, it is the age as observed by us, almost, but why would that mean it's not universal? Confused? The thing is, we can have one age for the entire universe to which most observers would roughly agree because the universe is pretty much the same for most observers. I mean, in the history of the universe, the conditions on a sufficiently large scale have been fairly identical. And so the passage of time as measured by different observers all having gone through similar conditions is again, well, identical. Even the beginning of the universe was a highly symmetric event. The Big Bang didn't really happen at a particular location, rather it happened everywhere all at once. So no location is anyway a center. Coming back to the current universe, everywhere we look, the universe looks the same. Not in our immediate vicinity, but zoom out enough and well, yeah, all directions are equivalent, a feature called isotropy. On distance scales of roughly 300 million light years, the distribution of matter is roughly the same. The universe on such scales is homogeneous. These features suffice to make the universe roughly age similarly everywhere. Now let's look at things from our point of view. The universe is expanding. Everywhere we see, things are moving away. The further they are, the faster they seem to be receding away from us. So shouldn't their experience of time differ from ours? Well, no, because this is not how cosmic expansion works. To start, even though to us it seems like distant galaxies are moving away from us, go to them and they'll say the same thing about us. There is this inherent non-specialness to the cosmic expansion. Every point is moving away from every other point. Plus, the cosmic expansion doesn't really cause any slowing down of time for any observers, because these distant galaxies aren't really moving away. It's the space between them that's kind of stretching. The time dilation from special relativity is about motion through space, not of space. An outcome of which is that there inevitably comes a point beyond which things seem to be receding away at speeds faster than the speed of light. Should that be possible in special relativity? No, but it still happens because they're not really moving, are they? That's not to say that the individual motion of an object doesn't play any role, but then think of how fast are these motions anyway. Ignoring the motion of Earth and the Sun and focusing on the galaxy, the Milky Way seems to be moving at around 600 kilometers a second relative to the cosmic microwave background, which is this background radiation that fills up all of space and is the same in all directions, a result of a highly symmetric universe, and perfect to decipher the true motion of objects through the Hubble flow. Now, the speed of the Milky Way is pretty fast, but then think of how fast light is. 300,000 kilometers per second. The speed of the Milky Way is about 0.2% of light, which is pretty fast, but then let's do the math. In special relativity, time as measured in a moving frame transforms via this equation, where gamma is the Lorentz factor, which is 1 over the square root of 1 minus v squared over c squared. For the velocity of about 600 kilometers per second, this gamma turns out to be around 1.000002. Now, so yeah, the galaxy is aging a little bit slower than the background, but then not much. Indeed, this is just the case for our galaxy. What about something that's actually moving at speeds much faster and closer to the speed of light? Well, obviously for such an observer, the measure of time would be quite different to the measure as observed by most of the rest of the universe, and therefore it wouldn't really be useful. And so the cosmic age is actually not the age by any such observers. Rather, we assume those ideal observers that don't have any motion in addition to the motion coming from the Hubble flow. These are the co-moving observers that flow with the universal expansion. The age as measured by all of these co-moving observers would be completely identical and therefore quite universal. It is in some sense a way of universal timekeeping, a time for the entire universe. Now, many of us would be bothered by it. It sounds a lot like the absolute time of Newton's. However, it's really not. It's not that everybody measures the same flow of time. Rather, these special vantage points that flow freely with the Hubble flow are really idealized observers that happen to experience the same passage of time. The rest of the universe that does have their own velocity through space would have their own personal measure, but it would not really be useful for anyone else. Yeah, so a change of timing. Which brings us to this idea that the reason we've been able to figure out so much about the universe is because the universe is so symmetric and at least large enough length scales, allowing us to talk about the story of the entire universe while sitting in a tiny, tiny, tiny part of it. Only because in our universe, all perspectives are equal. Just imagine if the universe wasn't homogeneous or isotropic. Not only would we lose this notion of one age for the entire universe, because it wouldn't really make sense as all the different regions would have aged very differently. There might be some that would be billions of years older than others. But also, we would have no clue to so many other things about the universe. All of our cosmological models are based on the homogeneity and isotropy of the universe, which also reflects that any deviation observed could lead to vast change in how we think about the universe. And nothing has been more important in that than the cosmic microwave background. The fact that the CMB is roughly the same in all directions makes it very much likely that both of our assumptions about a universe, homogeneity and isotropy, are pretty accurate. However, any anisotropy, if intrinsic to the CMB, which statistically there hasn't been many, could lead to vast change in how we tell the story of the universe. However, for now, we can rest easy, for there are cosmic observers keeping time while co-moving with the cosmic expansion, giving our universe one age to which we can all agree. Thanks for watching.